Sorry, wait. Okay, so then we move to the mix design and the fresh properties. So here is we are making the SACC use high early strength Portland cement and fly ash. And the water cement ratio is 0.3. So it is a normal, the typical, mixed proportion. And we use silica sand. Actually, you can use normal sand, but silica sand is better for the ductility. And SAP 1 and 2 with 0.3% and 0.6% by weight of the binder. Here, I need to mention that if you use SAP, you have the choice like with additional water in mix or without additional water in mix. So it depends on what you need. But we use those without additional water. And because it will absorb water from the paste, so we need to adjust the workability by adding superplasticizer, particularly, so if we use a high amount of subs, so you need to increase the SP amount. And fiber is normally used the PVA fibers from Corale. So here we compare it first the workability, the slump flow test of the motor without the adding fibers. So you can see here is a flowable, the cement, the motor, and we adjust by using the SP. So they are generally in a similar level of slump flow, but a little bit smaller than the normal, the no sub case. And also we test the bleeding, whether it's a bleeding because of the fiber and the matrix, but we didn't find any the bleeding, and the fibers dispersed very uniformly. And we test the compressive strength by using the SHCC, the samples. And you can see, compare with no sub case, so we measured 7-day and 28 days strength. And sub 1 and sub 2 by 0.3%, they got similar the strength at 7 days, but even higher strength for the sub 1 at 28 days. But if you increase the sub amount, so the strength start to decrease. So we think like the higher the 28 strength for SP1, the sub 1, is because of the higher absorptions. So then it will release more water for the intercurring so at later age. That means it's a densification of the pore structure at later age. But because of the swelling of the subs, you have some initial flows. So if you add too much, so you will have the decrease of its strength. And then we performed the uniaxial tensile test, like this one. This is our specimens, the dumbbell size, and very thin specimens. And you tensor uniaxial, so we can test the strength by using LVDT. So here is our result. Because of the high variation of the specimens, so each group, we did 5 specimens. So you can see there the strain and the stress relationship. So you can clearly see the tensile stiffening after initial cracking. But their trend are a little bit different. So seems like sub 1 case have the higher the ultimate strength and ultimate strength. That means the higher ductility. And each for all of the strength, here is one example. You can see many fine cracks at surface, and until the final localization of one crack. And then we compared with the from these graphs, we compare with the cracking strength and ultimate strength for these 3 cases. This is all of the sub 0.3%. And you can see, so the cracking strength, so a little bit reduced. But for sub 1, you have increased ultimate strength. And ductility, the ultimate strength. So sub 1 increased significantly than the no sub case, but sub 2 reduced a little bit. So we are considering that initially, so if you have because of swelling of subs, so you have the initial flows. that may reduce your cracking strength. But later, SAP will release water for further the hydration, particularly at the interface of the fiber. So that increase the bonding of the fiber. So particularly if you use SAP 1, so you will have the higher absorption. So the enhancing more for the find the bonding for the ductility. And here we compare with crack width distribution and crack spacing distribution. So no sub, and sub 1 and sub 2. Here I have to mention, so sub 1, so 5 specimens, we had one specimen missed. So only we count for 4 specimens. But you can see even that sub 1 have the more cracks than the sub 0, no sub. And sub 2 have the less cracks. That means low ductility. And crack spacing have the similar trend, like you use sub 1, so you have some more cracks, and with smaller the spacing, that means more densified the cracks. Okay, so then finally, so I want to talk about, because this material is very complicated, sometimes you need to do some simulation for the crack. So here is from research from Singapore. They proposed the stochastic model for the multi-crack performance. So they consider the different levels of multi-scales from one single fiber to the many fibers, the bridging effect and final micro level, and those parameters like matrix and fiber and interface can be use some of the parameters with random parameters. And they did some of the Monte Carlo simulation. So for the strain and stress simulation, and they can simulate the multi-crack, the random or uncertainty of multi-cracks for the high variation. And we try to adopt their method, and we represent their analysis like this. So 3 simulations, and you can see in each simulation you have different crack patterns. And then we use it for the 3 cases, the sub 0, no sub, and the sub 1, sub 2. So the red line is our analysis simulation. And you can see, so we try to optimize the parameters, some parameters, and you can see generally it gives a good fitting for the strain and stress relationship. So here is some of the micro parameters for those analyses. So one is like some are about the interface, some about the matrix. So like matrix, some about the initial cracking properties. So the raw value reduced. That means the more the initial inflows because of adding of subs. And meanwhile, so because of the interface may be in-housed because of the in-house of the bonding of fiber bonding. So that means our analysis is relatively reasonable. Our assumption is reasonable. You add subs, you may have the reduced cracking strength. But if you use it properly, and you may have increased ductility. Okay, so finally, I want to simply summarize it. So up to our current research, so if you use a sample, so sometimes you can have similar compressive strengths, particularly if you don't add additional water. But because of the initial flows, so crack strength decreases. But depends on the subtype. So it may in-house the fiber bonding, the interface. So finally, you may get higher ductilities. But those discussions should be furtherly confirmed by, for example, same observation for the fiber reinforced interface. And also in the future, we would like to carry out a self-healing and durability test. Thank you for your attention. That is all.
Thank you very much, Dr. Wang. So let's move to the discussion. Then one Zoom joining member raise hand, but can you ask, put your question Q&A, otherwise allowed to speak something? So, Akufas Jacob, do you have any question? And then now you can ask something if you want. Now I allow you to speak. No? Okay, if no. Okay, so how about others? So do you have any question? Okay, Farid.
Thank you very much for your nice presentation. Can you please come back to this slide 17? So you perform 3 numerical simulations. So we see different cracking pattern, but the tensile stress versus tensile strain relation is almost the same. It's not possible to find the variability that we can see in experimental results.
Yeah, this is just here it shows examples for the no subcase. No subcase. So you have the different cracking related to the that cause the different how to say ultimate strain. Sometimes so.
But you know, the curve is almost the same. You know, when we look to the experimental results,
it's not the same. You mean here?
Yes, it's not the same, but almost the same.
This is not the same. This is the three. You can the line. You can see.